So continuing the powers of 10, that's our pick and place, our probe station and wire bonder. So these are the tools to go from like bare silicon to probing it to packaging it to quick turn electronics.
Okay. Got it.
Once you have all the tools, it's all digital fabrication,
Right.
but printing we use maybe 20% of the time. There's a lot of other processes we use along the way to this fundamental digital fabrication. One of the most favorite processes is cutting and folding instead of depositing or etching. Okay. So this is Sam.
Hi, Sam.
Hey, Adam, nice to meet you.
Sam helped develop originally CAD and CAM for inflatable robots at Other Lab.
Oh yeah, with salt.
Yeah.
And now he's working in a sense, not what comes after, but extends it in places that can't go. So this is a 30-ton press.
Got it.
That we use for material testing. These are all sorts of machines Sam has made. He makes a machine of the week using the bigger machines, and it's to cut and fold. So Sam, can you explain and show?
Yeah, sure. I mean, 3D processes have come super far. I'm sure you've seen really cool stuff here so far, but 2D processes are still way faster and hyper efficient. So what we're trying to do in terms of turning bits into atoms is leverage things coming as sheet materials, doing two-dimensional cutting and folding processes that can then assist in the assembly of these three-dimensional forms. So say I wanted an airfoil wing. Here we can take and plot out in 2 dimensions a series of cuts and folds, and based on where we place them, we're addressing what the 3-dimensional shape looks like.
Again, to unpack, what Sam worked out was the math of this is kirigami, origami with cuts and folds.
This is a single sheet.
Kirigami is an inverse problem. You give him a 3D shape, he gives you the 2D cut pattern.
Right.
And for extra credit, he'll show you he can vary the mechanical properties. So you can make flexible as well as rigid structures.
Flexible.
Yeah. So I mean, you'll recognize this. This is a honeycomb core. They're used to make the lightest, stiffest structures, sandwich panels.
Wow.
But given that we have this addressability in 2 dimensions, we can produce structures that have a spatially varying modulus as we like.
That's not made as a bulk. That's actually made by cutting and folding the sheet.
Oh man.
So it can. That one's flat, but it can be curvy.
Right. This is like what all airplane floors will be.
Right, but you can make it out of any shape.
Right.
Right. And so then if we come this way.
So where it gets really interesting is where you actually tune the mechanical properties.
Yeah, so here we've got similar samples. So from the top, these look like hexagonal honeycombs, but they've got additional pleats here. So if we squeeze them, they have this mechanism where they shrink. And so by
let him feel this. So if you squish that, by where you put the cuts and folds, you can tune the stiffness of the material.
Right.
So you have a variable elasticity material made out of a sheet stock.
Got it.
Yeah. So then when we create these bulk volumes in the exact same construction I showed you with the wing, we can then sort of push on them and they give in a certain way. And based on this free parameter in the 2-dimensional cut pattern, we can control exactly how stiff they are. So here's a really stiff one, here's sort of a medium.
Oh, so what you're doing with your press is you're building a library of working your way into the flexibility that's needed.
Yeah, exactly. Making structures that can undergo large deformation in a resilient way is really hard. So that's what we're working on.
If you look at, say, my sneakers, there's a lot of different materials here. It takes about a year end to end to make the tooling to put it into production. There's a global supply chain of all these polymers, and there's trash when you throw it out.
And the specific energy intensity in the footwear industry is about 10 times what it is in the injection molding industry at large. So you look at almost 100 to 1,000-fold reduction in material energy input.
So you can start with a bulk sheet stock of a renewable material. You can turn it into a 3D form with tunable elasticity for the modulus. So again, these are just flat sheets. And again, this one is so stiff because the foams, to take this example, have to be pretty stiff when you stand on them.
Sort of
and you can make it all out of a single material.
Is there a reason that you can't just model this mathematically? Is this too complex?
Oh, we do.
You do?
We do model it mathematically, absolutely.
But you're using the press to check your work and make sure.
Absolutely. So I write a model, I have to do experimental validation.
Right.
And so one of the other tests So I showed you a static test here. This is sort of a very slow process. This is
now what he's going to show you. This is his machine of the week last week, roughly.
Right.
Okay.
So on here we've got a nice MEMS accelerometer. MEMS accelerometers have gotten tiny, such that for impact testers like this, we can actually make it completely embedded in the projectile. So no need for a big rail system. So I'll shut up and just demo. So if we do that, we get a dynamic loading curve at about 10 kilohertz.
So he just recorded the whole transient dynamics of that event,
Of it
Right.
hitting
of the
and-
impact,
so-
to study the dynamics of it.
if you
In fact,
look
so what he just pulled out is
here,
that kind of data.
So these are 4 different kinds of foams, and you can see the time scale here is on milliseconds, and we're retracing. So these are very repeatable phenomenon, but different foams respond differently under time varying loading.
And so what he's doing is he's, again, for things like this, cutting out the whole supply chain, and you just take sheet stock and plot and cold it. And so Sam, explain that machine.
Oh, so that's one of the original folding machines I made. So this,
So a folding machine?
yeah.
Well,
so this is I guess.
First, to explain how crazy Sam is, he concluded he had to make his own voice coil actuators to drive it. And so he spent a little while developing voice coil actuators, and then he decided he had to make his own back EMF motor controllers to move it.
So this is a cutting and folding machine. Here, there's a voice coil knife, just like a sign cutter, moves back and forth. And then there's a roll feed system here. So we've got 2 feed rollers and 3 folding rollers in the back. And let's see. Basically, by differentially driving these 2 motors, we can form any sequence of mountains and valleys that would be necessary to do this.
I
So the
see.
combo of cutting and folding in a single coordinate system lets us plot stuff like this out.
But when you want to do something like this isn't 1 pass. This is 2 passes.
So this is everything that runs vertically in this. Essentially 90% of these creases can be made by this machine
I
because they're
see.
straight and
Okay.
parallel, mountain, mountain, valley,
Right,
valley,
right,
mountain,
right.
mountain, valley, valley. And then the cuts can be made by this machine too. And then what you're left to do is gather it and skin it.
Right.
So you astutely pointed out, not an end-to-end process yet, but
Okay.
yeah.
I didn't mean to shit all over your awesome work.
No, in fact, that's the next step is to automate. This is 2/3 done. The third step is to automate that. Yeah, and so,
Let's
if you take these artifacts, you'd have a big machine with a long time
Yeah.
to produce what you can do here just by a couple quick cuts and folds, and you'll see more of that in the next space.
Okay.
All right, yeah, go ahead.
Okay.
Wow. Thank you,
Cool.
sir.
Yeah, nice to meet you.
Nice to meet you.
So now we're getting into bigger tools.
Yep. This is really big.
This is a Zund. One of these costs the same as 2.5 full Fab Labs. So you could buy 2.5 Fab Labs or one of these. And if you gave me a choice, I'd buy one of these.
Really?
This is we're in love with this tool. This is Grace.
Hi, Grace.
Nice to meet you.
Nice to meet you.
And so many of the things you've seen are made here. Vacuum bed, Kevlar belt, laser trimming, programmable interchangeable heads. One of them is a 50,000 RPM 3 kilowatt spindle. But what's interesting about it, it has all these heads that punch, cut, slice, roll. So all of the folded sort of stuff you've seen. So if we get some examples, these are objects.
That's made on this
Get some art.
machine. Oh, wow.
And so,
How does it cut through both sides?
so
You feed it through twice?
we'll show you
Okay.
in a minute. So if you take, something like this,
Right. Oh my gosh. That's insane.
if you think about milling or printing, you can just, or here, I'm going to grab something and come right back. Let's say, Adam, you wanted furniture.
Right.
So here, you can try it.
That's
Now, if you think about that, this took a few minutes to make.
Right.
Now, look at the cross section. This is flat, but it's being
Yeah.
extruded.
Yeah.
You have the hinges and the folds and all the shapes, and you look at the thickness of the cardboard. It would delaminate on the water jet. It would burn on the laser.
Yeah.
But by having programmable knives, you can slice and cut it and fold it. And there's been a lot of buzz about 3D printing a chair.
Right.
This is $1 worth of material in a minute or two of cutting.
Amazing.
So, Grace, can you show it in action?
Yeah, so I'll just cut this off.
Yep.
So I'm gonna run a job to try and make try and make a tube like this.
Okay.
So this will involve scoring, cutting, and punching. And we can do that with the set of tools that we have on here.
And explain why the tube.
The tube is good because when you stack them up, you have a material that's stiff in torsion but has some compliance along.
So we were given a challenge from the auto industry. They needed a material that, torque it.
Okay. Yeah, almost
But
no, but it's flexible.
And then you can bend it a little bit that way. And so
Right.
it's very anisotropic. And if you look at this volume,
directs force where you want it to
right,
go.
and you can fill this volume, again, with just a little bit of sheet material.
Right,
So
right.
go ahead, Grace.
Cool. You have glasses. Some reference bolts right now that it will use later on to figure out where the piece is when I turn it over.
And of course, it has a camera to adjust
Oh,
everything.
nice.
And then it's got all these different blades that slice, cut, roll, and so you can score, you can crease. When it comes off the machine, it's like that.
Yeah.
But this includes both.
Right.
And so the beautiful thing about this machine is you can very quickly scale up your...
Okay, I see.
Okay, you just triggered the
Oh, I'm sorry.
that's fine. You can,
I turned it off. My apologies.
You can quit production and we can use this stuff. So now I'm just getting it, so it's going to score twice.
And then it's a moving bed, so it can do this off to infinity.
Wow, on a roll.
Right. And then one other thing that's crazy is you've used large format mills with underlays, with sacrificial layers.
Yeah.
It laser trims everything so accurately that you can do high-speed machining in addition to everything else without needing a sacrificial layer. It
That's
just
insane.
stops right before cutting through. Are these, let's see.
Should just be able to pull it out. Yeah, there's some tabs.
And then how does it fold?
Well, you can probably figure it out, but we have the one, and we have the one. Oh.
That's half of it, right?
That's half, yeah.
Wow.
And then stick it together.
That's it. That's incredible. That is
Once you-
so
once you-
much fun. Yeah.
Once you
yeah,
get
yeah.
used to it,
Mhm.
it changes how you think about all your other tools.
I can imagine.
Like all the time you spent cutting and burning and extruding.
Yeah.
Okay, next
All right.
tool.
Next one. Thank you. Nice
That's
to meet
right,
you.
nice to meet you.
Hello, Will.
Good to see you.
And
see
as
you.
we go up in scale through the tools, I'd say the most pain would be if we lost that Zund.
Right.
But surprisingly, the one after it is this. So this is a wire EDM,
EDM stands
electrical discharge machining. And it's an interesting one. What this one does is that wire, let's see, that's a 4 mil wire?
Yeah.
Yeah. So that's a 4/1000th of an inch thick wire. It's like
about a hair.
about a hair.
Yeah.
And then it positions it to 1/1000th of a meter. And then this one can independently move the top and the bottom.
Oh my God! So it's
And-
multi-axis.
and multi-axis. Now, what's interesting is if it had one more axis, which is top, bottom, and rotate,
Yeah.
this would be managed like you manage tools for nuclear munitions, because this is how you make shape charges for nuclear bombs.
Really?
And so we bought it without that one axis, because then it has to be tracked as like national security. And of course, the first thing Will and Sam did was add the axis to it.
Of course they did.
Right. So what you can make on this
Okay.
is things like that. So Will, explain what that is.
Yeah, so these are little slots that I use to assemble these parts.
Remember
those
the
little tiny bricks.
Yeah, yeah.
This
Right.
is a
This
base
is
like- it's a
assembler
substrate,
for.
yeah.
Right, and so the wire EDM plots those out.
So the wire EDM comes in and cuts that and does that, and then
you
it comes
rotate
here
it.
and
Yeah,
does that,
exactly.
and it cuts this whole
Yeah.
thing. So it does
Yeah.
all of this cutting
Right.
Yeah.
at a nanometer scale.
Yeah. Micron scale.
Micron
Or these are parts, he's making micro motors. Micro motors for the micro robots. And these are making sort of channel extrusions for the flux pieces for the micro motors.
Do you wake up in the middle of the night and think, oh, I could do this other thing that I had?
Once we got this machine, it sort of like completely re-engineered
Yeah.
how I think
Now,
about
this is-
making things.
Just scrap left behind, but
Right,
like, you
that's
know,
a gear.
gears, bearings.
You know, I started out making things out of books, paper books, The World at Your Feet, the Alan Rose architectural models. And the moment I met a laser cutter, that's how I thought. And
Yeah.
so it was like, yeah.
And so what it lets you do is it lets you make the precision machine parts. So
Right.
you can make them not just the machines, but the precision parts of the machines.
Oh my gosh.
And so it completely changed.
We can,
Are you gonna run it?
Start it up.
No, but yeah. So is it already threaded?
Yeah.
Yeah. So of course it auto threads itself. It ballistically shoots the wire in.
And it has to do the machining completely submerged.
Right.
So what you see here is it actually sort of raises these walls and then fills.
fills that with water.
Yeah.
And it's very clean. It's just underwater.
So
And
it
again-
doesn't put out a hazardous waste when
Right.
you're done.
And again, it's like 4 mil curve. Oh, do you? Yeah. You want depth of cut?
Look at this. Look at this. This is what this machine does. That's the hole that it cut. This, what it comes through. Right? That's the thickness of a sheet of paper. And what is that? 4 inches. Holy cow. That's beautiful.
So again, in the powers of 10, these are few $100,000 machines.
So this is
Yeah.
putting electricity through the wire.
So it's amazing. It's this beautiful process. The wire's going through.
Right.
What's the voltage right now? It's not that high.
60 volts.
Only 60 volts, but the wire is so small and the gap is so small. That's enough to make a little plasma.
Right.
And so there's a little plasma around that wire burning away the material.
Just very
And
slowly.
When it comes off like this, that's the surface finish.
Right. Really? This is
That's how it comes off the tool.
That's crazy.
So again, in the powers of 10, you don't need this to make a machine. You need this to make the precision parts of making the machine.
Right.
So you just did what Will did. There's this moment where Will said, "Oh, wait a minute, I get it."
Yeah.
Like,
Oh man.
and once your workflow builds around this, you just sort of don't understand how to work if you can't do this.
Right.
And that was a real surprise. I expected it as a niche, not as like critical path.
But it's becoming a part of the.
Oh no, it is. Just almost every project involved, like Will's assembler, Sam's
Right.
origami machines. All of like the precision parts are made on these to be able to make those machines.
Okay. So what's next?
A minute ago, this was a cutting machine, a slicing machine.
Right.
Let's say, for example, you wanted to mill parts in 3/4 inch
Doeren?
Okay.
I love machining parts out of 3/4 inch Doeren.
Okay, so what if I just put this down? Further in,
Make sure it's past that line.
that's that line.
All right.
What if I put it down?
Okay.
And here, just that's just this is just flexible bed.
Yeah.
Okay, Sam.
Okay, so had my reference set.
Okay. So first it wipes its nose. It's wiping its nose.
And then it's brushing it off.
It's cleaning the tool holder.
Got it.
It's very swift.
Whoa!
It's picking out its tool.
Everybody should get hybrid.
This is like the Iron Man of tools.
Okay, now it's laser measuring the position.
Okay. Why is it moving back and forth just to get a...
It's just scanning.
Okay.
Okay, so it's laser trimming the position of the tool.
So it knows precisely where it is.
Okay, so now ready, watch this.
Oh yeah,
50,000
turn it
RPM.
on.
No way. What? And there's no dust or anything.
Say, where is the dust?
Oh my God.
It's like laser cutter speed.
Oh,
And
wow.
now it's a finished pass. Clean it up a little bit.
That's why you like this, because it is a Fab Lab in one machine.
Oh, vacuum off.
That's what 50,000 RPMs gets you.
Wow.
Waiting for the vacuum.
Oh.
Didn't go all the way through.
Oh, did I not set that correctly?
Oh, you
Sorry.
didn't go all the way through. But anyway,
Can't believe how
okay,
fast.
so
yeah,
it's like laser cutter speed
that's incredible.
with that, beautiful clean finish.
Yeah. Yeah.
Okay, next up.
Okay. Okay.
So you saw big machines.
Yeah.
Here's a big assembly space, and here these are precision machines. So these are like lasers. These kinds of lasers can do CO2 cutting, but also fiber laser cutting. That space is we're about to add a 3 kilowatt fiber laser with 3 mil kerf for laser metal cutting.
Nice.
Then we make a lot of use of these. These are small but precision mills with micron resolution. So we use those.
PCBs and stuff.
So one is
like that?
PCBs, but a big one also is machining machinable wax to cast elastomers to do quick turn tooling. And so in that you can cast metals or ceramics or all kinds of materials that you can't easily print or cut by making quick tooling.
Okay.
And then these are cool things, like this is an auto tool changing multi-axis sort of desktop precision mill.
Wow.
That kind of fills in these interesting intermediate parts of parameter space. And again, one use is direct machining, a big use, so like, let's see, oop, lost Joe's head. So like,
So this
that
can
was
cut
made on that.
That's an incredible resolution.
Yeah. So that's the point. These go down to micron resolution, so you can
Right.
make really precision parts. And again, a big use of them is to make tooling for quick turn production, to cast parts.
Right.
So in the same time you can 3D print, you can make quick turn tooling, and then make solid parts in high performance materials.
And this is machinable wax.
That's
yes?
machinable wax,
Yeah.
again, which you can use directly, but a big use is to make forms to cast. And there's metals and ceramics
Right.
and dense polymers that we use to, once you've made these sort of parts.
To do lost wax casting.
Well, no, not lost wax casting. I mean, you can do that, but what we do is we cast elastomers.
Okay, gotcha. Okay.
And then in that, there are all these great materials, again, like ceramics, like dense plastics,
Right.
like castable metal alloys, once you've made the production tooling. So in the same time to do one 3D print, you can make the tooling and then cast in multiple parts in high performance materials. So given that, you only print when there's complex nested structure you can't make any other way.
Okay.
And so then we do things like, there's $100,000 3D printers, but this is the Form 2 one of my students spun off. These are the waxes from a company we love to work with that just is a farm of commodity
They're
printers.
just going all the time.
Yeah, just as a commodity production farm. And then this is Ryan and Tom.
Oh,
Hey.
hello,
Nice
sir.
to meet you.
Nice to meet
And
you. I recognize that.
Well, so this is for you. We make a lot of use of sewing.
yes.
Tom's become a demon with the embroidery machine. He says he's been learning from old ladies on YouTube.
That's awesome. I just bought a brother.
Oh,
I just
cool.
bought a.
Let me know if you're looking for some tips.
Oh, I will. I definitely will, because I haven't even fired it up yet. It just arrived a couple weeks ago.
So Tom's been learning how to do that. But in addition to embroidery, there's all kinds of things you can do by, like the cutting and folding, by sewing, by cutting patches and sewing to make things like inflatable structures or tensile structures.
Right.
So we make a lot of use of sewing.
That is awesome. Okay.
Enjoy.
Thank you very much.
You're welcome.
I appreciate it.
So then you'll like this. The
yeah.
last stop is, this looks like an old-fashioned space, and it's an old-fashioned space, but it's connected to all the other ones. So in
Okay.
here, we do things like we lay up composites, both carbon fiber but natural fiber, natural resin. We use the big machine tools to make tooling. Then you come in here to lay up the composite.
Because you have the fume hoods and
all the exhaust. Or
Okay.
this we can do welding and foundry work, but one of the uses here is, again, you use the other tools, like the precision tools to machine machinable wax. And then in here you can cast all kinds of alloys or ceramics and fire them. And so you can do hot, dangerous, smelly things, which you can do by hand, but a lot of the use is based on the output of all the other tools.
Right,
and so what completes those tools is like laser metal sinter 3D printing. Cost $1 million for the machine and it fills a room.
Right.
But with a space like this, what you can do is you can make tooling and cast all kinds of beautiful metal parts.
And do something close to approximating it.
Well,
or-
it's actually the laser metal wins if you have dense, fine internal structure. This actually wins otherwise because you can make denser parts with better mechanical properties. It's harder to get really good compaction with the laser metal sinter.
Right.
And so it just depends on the geometrical complexity. But that's what this space is for.
I feel
A space you'd be happy in.
I feel very at home in this. I've always wanted a welding table like that.
Okay, good.
My head's about to explode.
So that completes the walkthrough.
Yeah.
Let me give you like 3 axes.
Okay.
So we just did bits to atoms and atoms to bits on nano molecular scale down to micro to meso to macro. So these are tools to go in and out. And they're actually all using similar processes, but over this wide range of length scales.
This is the greatest possibility engine I have ever witnessed.
So that's one axis.
Yeah. That's only one.
Yeah, so another axis in what we just did that's important to be clear is we just walked through, sort of think of it as $10 million in $1 million tools. Those are the research tools on like how you make the Star Trek replicator, literally.
Yes.
Within that, you can think of it as $1 million in $100,000 tools, which is the workshop to make the machines.
Yes.
So the $1 million tools lets us do the research. The $100,000 tools lets us make the machines. But within that is you can think of it as $100,000 in $10,000 tools, which are things like the 3D printers and the laser cutters.
Yes.
Those make projects. They can't reproduce all of their own parts, but they're good enough to make projects. That's what we use. I teach at MIT the How to Make Almost Anything class.
Yeah.
And that's what became the Fab Labs, and there's 1,000 now, doubling a year and a half. That's good enough to make almost anything. So that's the $100,000 scale.
Yeah.
And then within that, there's what you can think of as $10,000 and $1,000 tools, which is the machines made with the machines that can virally reproduce. And so the goal is the viral spread of the machines making the machines.
The machines becoming biology.
Which you can then develop in the Fab Labs, which you can develop in the workshop with the research. And so the powers of 10 nest, they all need each other. So that's the second axis.
That's only the second, okay.
And then finally the third axis is MIT made the first NC mill in 1952.
Yeah.
You can trace basically all modern machining or 3D printing to that. That's computers controlling machines.
Yeah.
Really interesting history. The second stage down that path is rapid prototyping of rapid prototyping, the kind of work you saw with Nadia, which is you don't pick a laser cutter or a 3D printer, you just compose a machine to do a project.
Right.
That's what we're just transitioning to now. There's all this attention to additive versus subtractive. That's going to get replaced by just rapid automation.
So all of the machines that you've got in here, you're looking to actually supplant them with this new generation.
Next step of rapid prototyping of rapid prototyping.
Right.
You assemble, it could be 3, 4, 5 axes, open, closed loop, additive or subtractive, but the machines keep changing with the projects. And you saw that today, and that's the next step in. That's still printing and cutting though.
Yeah.
The stage that comes after that is assembling and disassembling. And you saw the micro leg go up to the carbon fiber.
Yes.
That's what, so DigiKey stocks 500,000 types of resistors, 500,000 types of capacitors, 500,000 types of inductors. Will's assembler can make all of those out of 3 parts.
Right.
Conducting, insulating, and resistive. And with about 20 parts, we can make all the motors and everything else. So the assemblers gets rid of all of the different machines and all the supply chains and puts them in one machine. And the last stage is the kind of work Amanda and Noah showed you, is programming the materials. assemblers that assemble assemblers, self-reproducing machines. At that point, machines go away, and it's sort of like life in inorganic materials.
Right.
Now, this last axis,
Yeah.
what I just described was about the next 50 years.
Right.
But what's so interesting is they're all here today. You just saw all of them.
Right.
But they're not going to come out at the same pace. They're all here today, but over the next 50 years, we'll be going through this sequence of first, if you're fortunate, you have access to the tools, then everybody has access to the tools because they're viral, but you need all the tools. Then the tools merge into a single assembler, but you still need the assembler, and finally it can make itself, is what's going to be playing out.
This is a lovely vision. I want to come play.
Good.
All right.
Well, come
Thank you,
back.
sir. I appreciate it.